Hello and welcome to this MCMA webinar, Theory, Application, and Operation of Frameless Motor Technology. My name is Joanna Keel and I am the Manager of Marketing and Membership for the MCMA, and I'll be serving as your moderator today. Attendees have joined this webinar in listen-only mode, which means that you are muted. If you do have a question during the webinar, please submit them in the questions panel of your webinar screen, and we will answer all questions at the end of this webinar. This webinar will be recorded and a link will be sent to you within the next 24 hours. And now I'd like to introduce our presenter for today's webinar, Tom Wood. Tom is a frameless motor product specialist at Kollmorgen. Tom has worked with Kollmorgen for 30 years in various roles integrating motion control solutions as a machine designer, servo system customer, manufacturer representative, and high-tech distributor. I'd also like to thank our exclusive sponsors of today's webinar. Electromate. Electromate is a co-sponsor of today's webinar and the Canadian distributor for Kollmorgen. Electromate's core purpose is to help manufacturers build better machines using differentiated automation technology. They specialize in robotic and mechatronic solutions for the industrial automation marketplace. Respected by customers as a premier source for high-performance automation and motion control components and systems, Electromate specializes in servo and stepper motors and drives, motion and automation controllers, positioning systems and actuators, feedback devices, gearing products and operator displays, all supported extensive product selection, just-in-time delivery, dedicated to customer service, and technical engineering support. Kollmorgen is a leading provider of motion systems and components for machine builders around the globe, with over 70 years of motion control design and application expertise. Through world-class knowledge in motion, industry-leading quality, and deep expertise in linking and integrating standard and custom products, Kollmorgen delivers breakthrough solutions unmatched in performance, reliability, and ease of use, giving machine builders an irrefutable marketplace advantage. And now I'd like to hand it over to Tom to begin today's presentation.
Thanks, Joanna. This is Tom Wood. I also want to thank Electromate and Warren's team up in Canada for the opportunity to spend a few minutes and talk about frameless motor technology. Basically, the direct drive frameless motor story can be summarized in two simple slides. We have regular servo applications that use either belt pulleys, planetary gear heads, rotating nut and driven ball screw systems, all driven by servo motors that in some manner link to a mechanism, a machine, some kind of automation. And very simply put, what we're trying to do is to replace the electromechanical systems with as few components with a direct drive capability as you can see in this oversimplified kind of view. Let's take a look at a few simple points on why go to direct drive, why go and pursue frameless motor technology. In the need to generate clean mechanical assemblies and get lower and lower parts count, the reduction of assembly time, also trying to make sure that in taking advantage of frameless motor, we get significant improvements in servo performance. Due to reducing the lost motion, the backlash, and the losses in motion control associated with gear trains and the mechanical systems, we can see system accuracies increase up to 50 times. By having higher and higher servo performance and machine control bandwidth, we can get into the capability to push the bounds of the motor and architectures and technology. Historically, there's been a need to worry about when you applied a servo motor due to lost motion and due to inertia mismatch. That's the load inertia reflected back through the motor inertia. We've always wanted to have kind of a rule of thumb of 5 or 10 to 1 motor load to load of the machine matching. This was due to trying to make sure you could get a good, stable servo performance. By going with direct drive technology and reducing or eliminating all lost motion in the system and having an extremely stiff system, this is where we get the increase in servo performance. Also, you'll have very little maintenance, typically with no belts, no gearing, no lubrication, no leakage. these are systems that make sense and good solid reasons for going direct drive. Because of the lack of mechanical transmissions and the additional parts, there is a significant reduction in machine downtime and improvement there as well. Another benefit of going with a frameless motor architecture is that we often have the ability to have a through bore through the center of the shaft of the motor. We will now be able to bring in functionality like process air, dealing with having pneumatic systems come through. Even hydraulic systems, oftentimes in applications, we see people putting large bore assemblies for slip rings and even microwave antenna systems through the center, often in military and aerospace applications. The other performance improvement is that we can generally run substantially more quiet. We've seen improvements in noise reduction by up to 20 dBA scale. And this, of course, is by getting away from having those typically high-powered, high-performance servos screaming at 4,000 to 8,000 RPM, driving through gear trains that make a lot of extraneous noise, and to get these systems quiet. In the European model of machine building over the past 15 or 20 years, they were very quick to adapt and develop machines that had frameless motor architectures. In the United States, we were somewhat slower in developing this because we had very large floor spaces on the manufacturing centers, and we weren't as constrained by having physically large machines. The use of lean manufacturing processes in most of modern American manufacturing environments has caused the need to have machines physically get smaller. And as a result, the direct drive nature of motors and designs has been significantly improved. I want to spend a minute on one particular style of direct drive application that is basically taking a housed, simple, directly driven, frameless style motor onto a 4-foot diameter steel load wheel. This particular load wheel weighed 250 pounds, and there are 96 steel elements at the near the edge of the radius of this system. And this would have been for an application, I'll generically speak to it as, let's say there would be a need to very specifically put a needle into a process point near the radius here. So we've got a move of 3.75 degrees per peg, and you've got a 15 pound-feet second squared total inertia. The inertia of the load to the motor in this case was over 1,500 to 1 load inertia. You'll notice that the motor has a continuous performance of over 250 foot-pounds. Frameless motors are sized anywhere from 1 to 1.5 inches in diameter, all the way up to, we have standard housing systems up to 34 inches in diameter, with continuous and peak load points from measured in ounce inches up to measured in tens of thousands of foot-pounds. If I take a look at the move profile that this particular application was able to accomplish, the nesting of the load points for here had to be accomplished very quickly, and especially with a high load inertia, trying to get down to a settled move time less than 100 milliseconds. This is actually a plot directly from a scope function we have in one of our drives that allows to show both the actual and the commanded velocity. And you can see how nice and clean the velocity profile is here. And then the motor current shown in blue here, that's showing exactly the kind of path you've got and that little bit of tail trying to drive out the very last of any settling time in the application. So you'll notice here, for example, that we've got 100 millisecond move time, and that coupled with an application that is driving, let's say 100 milliseconds of actual performance, that's 300 cycles per minute for the application for this kind of move. I'm going to show a little bit of information here on a repeatability test that we did. I'm going to show a bar clamped to that rotary table at a point 26 inches in the radius from the center. I'm going to put a dial indicator, and this dial indicator, the numerals here are going to indicate a thousandth of an inch, and each of the will be a 10,000th. That 10,000th of an inch is representative of 8/10 of an arc second per division. So the dial indicator you see here on the system is mounted to a steel extrusion bar, and we'll then go through a process of zeroing it out. And in that, you'll notice here that it's 1, 2, and 3 thousandths of an inch by the large numeric indicators. Each division is 10 thousandths of an inch. And let's take a look now as we command the motor to draw back and forth to move away from the zero position. And moving away from the zero position clearly takes it off the dial indicator and will return. And now we're going to show the variance of well less than 1/10,000th of an inch, or better than 8/10 of an arc second of repeatability. Keep in mind this is done at a radius of 26 inches from the center. We're going to move the motor away in just a moment here, and we're going to put a piece of Scotch tape onto that. And as we bring it back into position, you're going to see that the thickness of the tape is on the order of 1.6 or 1.7 thousandths of an inch. As we back it off the position and remove the tape, you're going to see it return to that same zero location. So again, the stiffness of the system, you'll notice, if we push on the load wheel, we only see about 1,000. We push on the extrusion, you see as much as 3 thousandths of deflection. This is showing that the servo loop has a substantially higher stiffness than the steel extrusion itself. This kind of system you can see has extremely high bandwidth and extremely high servo performance. Right now we're commanding 1/10,000th of an inch moves, and when a hand is resting on the dial wheel, you can't even feel the physical movement of the system. This shows the capability of high performance, direct drive kinds of systems, and it kind of typifies extreme positioning capability within these kinds of systems. Various kinds of frameless motors that we might see would be everything from large diameter, that longer, skinnier style form factors that are more like traditional servos that might have speeds up to perhaps 15 to 20,000 RPM in some spindle applications, and frameless motors that would be in a form factor more like a pancake style system. These motors vary in performance, and basically most any kind of servo motor can be adapted and developed into a frameless motor architecture. Applications for these, we'll go through several different types. Probably one of the most popular and highly visible applications you see on factory floors today is the use of collaborative robots. These collaborative robot designs use frameless motors integrated into each of the joints. So you'll see waist, hip, shoulder, wrist, and often distal joints are run with small frameless motor applications. These motors are embedded in machines that, in the particular sizes we're seeing here, have the capability of rapidly and accurately positioning 5 or 10 kilogram loads. The application of similar kind of robots we're seeing in surgical robotic procedures. Again, the same kind of applications, sometimes using direct drive, sometimes driving small gearing systems that allow for very, very high ratio and yet higher speeds of the system. The outcome, of course, is still a highly stable end-of-arm effector, whether you're dealing with some kind of cutting elements or whether you're dealing with some kind of positioning relative to industrial automation requirements. Very often we'll see special purpose motors, in some cases in semiconductor wafer handling machines. Sometimes we have to adapt these motors into special environments that might have everything from vacuum rating in systems, and we'll typically see applications in excess of 10 to the minus 6 or 10 to the minus 7 torr. We'll also see applications where these kinds of motors need to be space rated or have radiation hardening characteristics. Very often in those applications, we'll find the ability to use a recipe that allows us to get rid of certain polymers, getting rid of some of the cross-linked polymers that can add problems to long-term life and sustainability in the motion in applications that don't take those into account. We'll also see use in manufacturing automation. And it isn't just end-of-arm tools like you see in the example image here. Also, general conventional machine developments where we use direct drive motors, everything from replacing the the belt and pulley systems, replacing the motors that are driving ball screw actuators, or the simple replacement of conventional planetary and spur gearboxes driving systems. The idea here is that the trends of these systems, those machines are generally wanting to be smaller and smaller. We also see in the machine tool environment where people are adding additional axes of high precision automation. In the case of some gear cutting and hobbing applications or in other specific machine tool processes, the use of extremely high bandwidth, very precisely controlled motion allows for tool holders to work relative to machine tools. Oftentimes applications are asked to go into somewhat unusual environments. Back in the 80s, these kinds of motors we had employed when we were working with Woods Hole. We were involved in the development of thrusters and actuators for deep sea work. So these motors are sometimes put into applications where they are oil-filled and pressure compensated to allow them to go into regimes that are 2 miles below the surface of the earth and to downhole oil and gas applications, or perhaps 4,000 meters below the surface in the water, again with 20 to 30,000 pounds per square inch of pressure that the motors might see. The extreme environments that might go all the way into space, where we have applications. We've been on multiple of the Mars rover programs. We've been on the upper torso humanoid robot on the space station. So your applications may not be as extreme as these kinds of applications, but the capability to adapt frameless motor architectures and technology to the application should be quite sound. Another very strong element we're seeing in today's market is electric motors replacing hydraulics. The weight that you have to deal with when you have an HPU or hydraulic power unit, as well as all of the heavy-duty cables and the elements of driving the electric hydraulic motor, hydraulic motor systems, you'll find that the reduction in weight and the reduction in operating costs, maintenance, and the potential improvement of the environmental sensitivity that some have to spilled hydraulic fluid. Not only do you have relatively low temperature flash points for the potential for fire, but also in many food applications you'll find that they can no longer use hydraulics to have any kind of proximity to the food manufacturing processes. The use of frameless motors and embedding them into machines and allowing them to be into cleaning environments, high pressure, high temperature kind of spray. The hygienic uses of servo motors like this are also very prevalent. We were approached a few years ago by the National Robotics Engineering Center in Pittsburgh, part of the Carnegie Mellon Group, and these folks asked us to help them to develop some motors that would be extremely torque and power dense for an application. The Fukushima nuclear disaster led to an understanding that we had to have robotics capability to go into environments that were not able to be served by humans due to the extreme nature of radiation or perhaps temperature, other elements that became problematic. So Kollmorgen, within a relatively short period of time, worked to develop 4 separate motor packages that the NREC team integrated into a solution that included a high-ratio gearbox, a torque tube transmission system through the design, a high-resolution feedback device, and a braking system that allowed for over 40 degrees of freedom on the so-called Shimp robot that they had that was in the top 3 of the DARPA Robotics Challenge. This was the only robot that was completely designed and developed within the 18-month time frame of the initial DARPA challenge. And we had over 40 axes on this, all developed using these same 4 building blocks. The idea of closely integrating frameless motors into gear, transmission, feedback, and brake systems is exactly what a significant number of our customers do for their own automation and robotic applications. I'm going to take a moment and show a very basic mounting video. This shows the manufacturing simplicity of assembling a system that has a package. In this case, we have a company that uses a liquid cooling jacket on the assembly. And you can see that you've got motor wiring and a porting here for allowing the cooling. Because this is being used at the end of a robotic arm, they needed to have a very, very high performance motor. In this case, these motors spin up to 15,000 RPM, and that particular motor that you see in hand there is up to 8 horsepower peak and 5 horsepower continuous in the application. So let's take a look at the mounting practices here. The stator assembly shown here is going to be bonded into the housing, and they scarf it using an 80 grit sandpaper. That's a method to make long grooves. And after cleaning and priming the system, one of several potential industrial adhesives, in this case a 409 Loctite, applied inside and outside the stator sleeve. The stator is inserted into the housing and rotated to distribute the compound evenly into its final location. In this example, the point where the rotor leads will exit the housing. When done vertically, the hydrodynamics of the adhesive will naturally center the stator inside that housing assembly. The rotor is going to be clamped onto the shaft using a locking ring assembly. The shaft has been machined using standard machine tolerances. The bearings are then added to the shaft, and the assembly is pushed together. The shaft is then balanced. Because this one's up to 15,000 RPM, typically balancing is recommended for shaft speeds in excess of maybe 4,000 or 5,000 RPM. The completed assembly is pressed into the housing, relatively low magnetic forces here due to the relatively small motor size, and now the motor is ready for its final testing. It's a bit of an oversimplification, but it is very straightforward and meant to show that the process of integrating a frameless motor into a fairly conventional industrial automation system is very practical, simple, and even in a relatively fistful-sized motor, does not have magnetic forces that would preclude the typical manufacturing company for becoming, in effect, a motor builder. Let's talk a little bit about motor form factors in frameless applications. There are basically 2 types of frameless motors. The classic torquer motor shape, or pancake-style shape, is exactly what it looks like. It is relatively thin in cross-sectional profile and perhaps a little larger in diameter. A servo motor style shape would take on the form of having a longer, skinnier form factor. Typically, a much smaller through bore is available and a lower pole count to the system, which is also indicative of the relatively higher speed that these kinds of servo motor shape frameless motors might involve. In both cases, the outer portion of the motor is typically non-rotating, and we call that an armature or a stator assembly. The internal rotating element is typically a permanent field device and is called a field or rotor assembly. The same is true of either style machine that you see here. An interesting rule of physics comes into play when trying to adapt frameless motors into machine designs. We call it the D squared L rule. And you can quite simply say that, hey, look, if you double the length axially of a motor, you're going to have an increase in continuous torque and typically power that's roughly proportional to that increase in length. So double the length, double the continuous torque. But if you, instead of doubling the length, if you were to double the diameter that you see in the system, you don't just double the potential for increase. You actually, it's a squared function of that increase. So in this case, your continuous torque would be 2 to the second power, or squared. You would have 4 times the continuous torque capacity by simply going to the larger diameter. This is why when you go to pick a motor in a frameless motor application, if you have a form factor to deal with, you generally want to try and maximize the diameter, and that will shorten the stack length and give you the best effect of performance improvement. So, largest practical diameter, very often the way to start initiating the application. Obviously, you've got to take into account torque and speed load points, duty cycle, temperature details, understand what limitations you may have from the amplifier, whether it's certain bus voltage or current levels that are available from the amplifier of choice that you've used. The mechanical envelope that you've got is clearly going to define what the maximum diameter, maximum length, the through bore requirements based on elements you've got to have in your process, and the type of mounting you plan to have, whether or not you're going to have a permanently mounted rotor and stator in your design, or if you're going to have a system that allows for removable for either maintenance or other process control applications. Those stack length changes are going to give you appropriate increases in wattage. We're also going to be able to optimize the winding parameters based on exactly the current and voltage available for the drive and for the application. These choices would vary from groups of pre-engineered standards that would be the fastest available, all the way down to custom systems where we want to highly optimize the package. And in some cases, to push the performance improvements using some kind of liquid cooling in an application, you'll find that we can build systems. Either we can have half-shell cooling systems, we can have customers more often will simply develop their own housing, as you saw in the video a few moments ago. Another question that comes up regularly is, what about position feedback considerations? In a conventional motor, I already have a shaft and bearings, and I simply apply a feedback device, whether it's resolver and encoder, to the back. The same kind of feedback that you use in conventional servos would come into play in frameless motor applications as well. The use of encoder, resolver, whether it's absolute or incremental systems, they're all available and can simply be used in the same manner as you'd use them on the servo. They would simply be mounted at some appropriate shaft location on the rotating element that's being directly driven by the frameless motor. Sometimes a resolver is a very practical way to go. Typically a little bit lower in resolution, typically only about 16 bits of resolution, but very good for high shock and vibration applications and high ambient temperature applications. Oftentimes military applications and downhole oil and gas, other extreme environmental requirement systems will use resolvers. Resolvers have standard options available with up to 140 millimeter diameter and as big as a 93 millimeter through bore in the center with standard shelf available components. Encoders are more and more robust and are able to sustain operation in higher and higher ambient temperatures. We're typically seeing encoders these days be able to operate up in excess of 100 C ambient environments. And now they're, instead of having typical shaft-mounted style encoders that would be coupled to a rotating shaft, now the idea of using large through-bore encoders that let you take advantage of the through-bore frameless motor design are available up to 390 millimeters in bore. So you can get very large processes, slip ring assemblies and the like, all through the middle of these systems, or have very large access into the middle of systems and yet maintain the integrity of very high position resolution. In excess typically of 22 bits is commonly seen. Also, there are relatively low-cost frameless motor applications that are available with magnetic style encoders. And the magnetic encoders, in this case, do not have problems with any of the stray fields from a frameless motor, even mounted in close proximity, because those kinds of stray fields generally are away from and not overly strong to impart any problems to the motors for the to the encoders on these systems. There still is a lingering concern on how do I go ahead and put these things together? How do I mount these components into my machine? And what I'd like to do is basically to say, look, you as a machine designer, you understand the dynamics of how your shaft has to operate in your application. You understand the dynamics of rotating that shaft, the dynamics of the bearing considerations. You understand the machine tolerancing and the precision of the elements that go into the mechanism. I'm saying that your shaft, your drivetrain, and your bearing system is more important than the mounting requirements for the individual components of the frameless motor. In fact, the runout that you have on your machine, let's say you've got a rotating piece of equipment, the shaft is going to be rotating at a couple thousand RPM. You're going to be seeing an application, and your typical design is going to be somewhere within 2 or 3 thousandths of total indicated runout, or TIR. If you're greater than that, when your machine is running at speed, it's going to dance across the floor. You obviously don't want to build a machine that's going to have inherent inefficiency or balance issues. So you're going to build your machine with tolerances that are going to hold you inside that 2,000ths TIR. Give you an idea, the air gap needed on our frameless motors is typically, and this is the radial running clearance, the OD of the rotor compared to the ID of the stator on both sides. Our 2-inch motor has 15 thousandths of an inch of air gap. And although we'd like to be as practically centered as we can, if you're maintaining the integrity of a couple thousandths of TIR, you and your manufacturing practices, your machining tolerances are going to be well within the manufacturing tolerances required for building and integrating a frameless motor into your project. Let's do a quick analysis on a little CAD view of how a mounting example might be handled. So I'm looking here at let's call this half a system, because I only have one set of bearings in here. There would be in your machine, this is simply a housing element in blue that would be containing the motor and the shaft bearing for one half of the system. I'm actually showing in this example a little bit of in this case, a through bore encoder as well. Let's blow this apart a little bit and pull out the shafts and rotor. I want to further now pull out the stator and pull off the rotor from the shaft component. Let's dive in a little deeper and take a look at what we might want to do in an example of using an industrial adhesive or bonding. Using today's high-performance bonding adhesives, industrial adhesives, is often found to be the most practical way to manufacture these kinds of systems. So let's take a look. I'm going to go from a 3D to a 2D to a detailed view in black and white here. And I'm going to go into some specifics and details here. So in this mounting example, mounting a frameless motor stator, in this case this is the electromagnets and the larger diameter piece, you'll notice we'd have machined in depth stop features. You would have the machining that would allow for a slip fit. This allows for ease of manufacturing handling. You're not having to deal with things like shrink fitting. You're having to deal with heating or cooling elements to assemble these pieces together. And in fact, you'll notice that there is a couple of channels that we have recommendations for allowing additional adhesive to be maintained inside this groove, typically as much as 50% of the surface area here. You'll notice that that depth stop feature would allow for making for minimum end-turn housing clearance. This would be important, especially when you're trying to maintain the integrity of the creepage and clearance limitations to make sure that your mechanism will be within general practices and best practices for CE, UL, CSA kind of capability. We will be able to provide you with the files that show that our motor elements are designed with compliance to these standards, and that you, in using best practices, will be able to further have your system's compliance as well. We make some specific recommendations for structural epoxy, some of which are ambient set and take a longer time to set, and some are actually temperature or thermal set and are typically done in an overnight time in an industrial oven and ready to go and cooled by the time the next morning shift might start. So this kind of detail is also available in the selection guide documents and mounting practices guides that we've got online. This again is something you'll be able to review if you feel like you would like to on the MCMA website over the next year as well. For dealing with bonding the rotor to the shaft, we typically see that something as simple as a retaining compound, like a Type 640, would be appropriate. Now here, we do recommend a precise location slip fit or a little bit tighter tolerancing on the parts, but again, this is well within the typical manufacturing means of applications and machine developments that our customers see. You can, of course, deal with bolt-on configurations if you need to have a more removable style system. So bonding with structural adhesives, really key that it's dependent more on the customer machine requirements than on the frameless motor mounting requirements. They're very cost effective. In fact, the structural adhesive has a further benefit of being actively able to stand a wide dynamic thermal range. If the application you're running your machine might be cold at one moment and then with motor executing getting very warm, it turns out that through many, many thousands of cycles, the bond line of the industrial adhesives actually creates a stronger and better joint than the potential over a similar wide temperature range that you might see in a shrink fit style application. So again, we actually recommend the use of structural adhesives all the way up to our largest motors that then are only recommended for use with clamping or bolting. And all that information is available with typical frameless motor manufacturers in their selection guides or in their mounting guidelines. Let's take a quick look at the clamping and bolting example here. And you'll see that we kind of blow apart the application, showing, again, the bearing and the feedback device on one side of the housing. The clamp ring, you see here, shows, and it would be different number of clamp ring bolts that are evenly spaced around. Let's go from 3D to 2D and down to a detail view. And here, just making sure that the gap behind the clamp ring to make sure you've got allowable compression. Same kind of depth stop feature and end turn dimensioning. Very simple. Again, we've got a precise location slip fit, and the clamp ring has got to engage a significant portion of that stator shoulder in here to be effective. You'll find that similar details are identified here, so you'll be able to review this at a later date as well. In clamping and bolting, again, very straightforward. We have the ability to not only vary the ID of virtually all of our frameless motor rotor applications, but also can provide specific bolt-on or in some cases through bolt hole configurations for mounting the rotor. Very straightforward, and the performance of these systems is not going to be hindered by your ability to manufacture these in the application. Sometimes we do go outside of standard catalog motor offerings. And what happens if we've got a thermal limitation and we've got to get in and look at a specific ambient temperature or an amplifier capability? It turns out that one of the things that we can do is we can actually provide to you the ability to look at a performance curve generated by the actual application requirements that you've got on your system. What I'm going to do here is I'm going to pull in a live view. This is on the Comorgan Developer Network website, and we're going to be turning this on live for all of our customers to be able to use. And we're going to be able to have two different families of our conventional servo and torquer motor, frameless motors available, be able to pick frame sizes, be able to pick stack lengths, and be able to pick standard windings, and to show, based on a given ambient temperature condition, allowing you to set a maximum winding temperature in the event that your process was limited to the thermal capability of the motor. You may want to only have your winding temperature get to a point of, let's say, 100 degrees C, as opposed to a maximum of 150 that's allowable. We would also have the ability to show whether or not the system, what it would look like with a liquid cooling, and be able to give you some indication of the amount of watts you'd have to dissipate to improve the continuous performance of the system. By dealing with liquid cooling in an application, you do not increase the peak torque capacity of a motor, but you do generally see an improvement from 50 to 80% of the continuous torque capacity of the system. So the other thing we'll be able to deal with is to look at variations in the input voltage. Whether you're dealing with a sine wave style input and you've got, let's say you've got 230 volts AC coming in, that's going to create a 325 volt DC bus. Let's say your amplifier, right now we're simply showing what the motor performance is here. If my amplifier only had a 1 amp capability here on the system, you would notice that the continuous torque is limited now by the continuous of the drive. And it produces a curve that shows a similar kind of peak torque, but now a reduced continuous torque simply as a result of the drive limitation. So if you were back up and had a 2 amp drive limit, you would see this thing live as well, would go back up to just the 1.73 amp that motor would allow it to run at, which is what you see up here. So these kinds of variations, this kind of tool to allow you to optimize the performance of your system based on input voltage, based on actual amplifier peak and current, peak and continuous current capability, based on liquid cooling versus not liquid cooling, you'll see this improvement is fairly substantial. So as a result, these kinds of tools, let me drag this back off of here, these kinds of tools give us an ability to generate optimized performance. I expect we're going to have this online within a month here now. So how do I get to the understanding the performance requirements of a given system? On the Comorgan website and many others, it turns out there is the ability to create specific analysis tools for the mechanisms that you see, for lead screw, conveyor, rotary, direct input kind of elements, nip rollers, even rack and pinion systems, to develop specific torque and speed profiles that will allow you to get a good starting point for your project to understand the requirements of torque and speed. Not only will you be able to put the inputs in for the mechanical assemblies that you'll be developing, but you'll also be able to program into the analysis here the specific move times, speeds that you want to achieve, the rates of performance, and the duty cycle, and this will help generate motion profiles that will make, hopefully make a difference for you. Well, it turns out that I've taken 45 minutes of time here. I certainly appreciate the opportunity to have gotten together. And I think, let's see, if there, Joanna, were there any other questions you wanted me to work on?
Yes, at this time we would like to open it up for questions. And again, thank you, Tom, for that. Got quite a few that came in, so if you do have a question, please feel free to put it in the questions panel of your webinar screen. We will take some time to get to those questions, and if we don't get to everyone, we will follow up with an email after. For your first question, Tom, I'd like to ask, one that came in is, how hot does the motor get? And do I have any special design considerations as a result?
That's a good question, and in fact, let me pull up. I've got some stuff over here I can pull up. Just take me a second. I think one of the key things that you'll want to try and involve with is that we have the ability to deal with taking applications to high temperature because the motors can stand it, but sometimes the processes themselves can't stand it. So we can actually embed in the system thermistors so that during the time of development we can see exactly what the actual temperature at the application is. It turns out that with either an avalanche style thermistor device that might be used to self-protect the application, self-protecting the drive, we don't get really good technical information on what's actually going on, but we have an option for linear thermistors that give us the ability to go in and monitor the actual temperature of what the motor is producing. This allows you to either deal with limiting the performance of a motor to maintain a temperature within a certain dynamic range. This might be important for things like manufacturing processes that are thermally sensitive, or in medical applications where you don't want to have a housing on a particular machine design be too hot with proximity to, let's say, a surgeon or to a patient. So by understanding through the prototyping phase exactly what those thermal levels are like, we can appropriately size the motor, getting enough thermal mass and performance in the motor itself to make sure we don't have too high a temperature limitation in the design. I also notice here too that there are questions on here's another one on peak torque heavily influencing wire heating and magnet heating as the motor heats up. I want to say that in fact we can determine through some simple tools and analysis, depending on the duty cycle of your excursions into the peak torque range, we can see that the motor will, over a period of time, tend to stabilize thermally at certain points, or, depending on the duty cycle, might be hot for periods of time. And this can be determined right here by actual means of proof of concept in the initial prototypes, or we can actually model some of these things through some dynamic tools that we've got, some FEA tools and others that we've got in advance of actually cutting steel and putting systems together. So hopefully that'll address some of that. I think, too, I'm reading some of the questions here on the side, Joanna, so I'm going to take another one here. The magnetic field, does the motor that obviously has a strong magnetic field, does that have any problems with influencing things near the and in fact, one of the things you're going to find is that installation of frameless motors is probably the point at which you see the influence of the magnetic field strength to be the most significant. In our mounting guide papers that we've got, there is an actual table that shows mounting force summaries for both radial and axial forces that can be expected to be incurred when you see the proximity of the rotor and stator coming together. In some applications, the forces are minimal, and you may see, in this case with our 2-inch motor, that axial force and the attraction force that you'll see when assembling those motors per inch of rotor stack, you're only seeing about 20 pounds of attraction force at a worst case. That being said, take a look at what the numbers are with some of our largest motors. That 34-inch diameter motor with a multi-inch stack length can see thousands of pounds of attraction force. And the need for the use of jigs and fixtures and tooling to allow for the careful installation of these kinds of systems is very, very practical. These are the kinds of analysis elements that we help our customers with ahead of time to make sure that they stay out of trouble in terms of the manufacturing processes. I think we've run down on time here now, but Joanna, any other comments or questions?
Yeah, it does look like we're getting close on time. So again, if we didn't get to your question, we will follow up with that at the end of this webinar via email. And again, Tom, I wanted to thank you as well as our participants today, and of course our exclusive sponsors, Electromate and Cole Morgan. And as a reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you within the next 24 hours. And again, if you did have a question that wasn't answered, we will follow up with that via email after this webinar has concluded. Again, thank you for your time, and be sure to visit www.motioncontrolonline.org for a list of our upcoming webinars. Thank you, and have a great rest of your day.